Swayam Prabha. Digital India. Educated India.
In the last lecture, we had looked at some of the issues in the location of facilities, and we had got a broad overview of the problem of location of different types of facilities. In this particular lecture, we are going to be talking about some mathematical models for facility location. In fact, before we take up any mathematical models, just to initiate the discussion, I'll discuss a case study. This particular case study is actually based on a paper that Professor Premvrat and I wrote, and this is the reference. It's called a decision model for a multi-objective plant location problem. And the basic intention in this particular case study is to look at the various factors which are relevant for the plant location problem, and try to then determine, after conducting a feasibility study, as to what should be the best location for the manufacturing plant. So this would be the kind of study that any new entrepreneur or any new company contemplating a new location for a manufacturing plant would go through. In this particular case study, the objective of the location was actually to set up a straw board plant. Straw board, as you know, is packaging material which is made from industrial waste, and basically the idea was that this would be set up in an industrial setting, so that there would be availability of industrial waste automatically, and that particular industrial waste would serve as an input for the plant, and this would then be processed to supply various industries needing packaging material in the form of cartons and so on, various things. So this was the basic idea behind the location of this particular plant. Now, what was actually done was that in order to conduct this study systematically, interviews were carried out with the plant managers and with various other people in the organization to identify what were the various factors that they considered important for this particular decision. And after a series of discussions with the management, it was found that the factors that need to be considered are: A, nearness to raw material source. Obviously, the nearer you are to the raw material source, it would cut down on costs of transportation, and it would also be easy to get your raw materials. The second factor was that was considered important was availability and dependability of power. Then the managers identified transport facilities as an important factor. Labor supply was another important factor. Employee facilities, the kinds of facilities that employees will have in terms of shopping, recreation, schools, etc. This was considered to be a factor in the beginning. Competition for the market was considered to be another major factor, because if there were already a large number of manufacturers of straw board in that particular area, it would be difficult to sell your product. So competition, the lesser the competition for the market, the better it was. Nearness to market was considered another important factor. Government incentives. You know, typically the government might want to give certain kinds of incentives for certain locations, maybe to encourage development of certain backward areas, or so those kinds of things. So these are the kinds of incentives that are they available. And then finally the cost of land at that particular site which you are considering. In fact, you see that these factors are almost generic. In any plant location problem, you would have to consider these various factors. The only thing that would happen is that the relative importance you might give to these factors could vary depending upon the nature of the plant. Our approach in this problem is essentially something very simple, and it is summarized in the form of this table. What we would like to do is we have identified the objectives that we have. We would like to prioritize these objectives and give certain weights, and then we identify alternative locations A1, A2 and so on up to AM, and each alternative location is evaluated on the corresponding objective. For instance, P11 is the score given to the first alternative on the first objective. P12 is the score given to the first alternative on the second objective, and so on. So if we can then get these scores somehow, then what we simply have to do is we can calculate the effectiveness of alternative A1, alternative A2, alternative EM if there are M alternatives, and get a kind of a score. This is very similar to the manner in which we evaluate students in a class. So you can interpret this as these are the candidate location of the candidates, and these are the performance in various subjects that you go through, and each subject has different weightage or different number of credits, and what we assign basically to you is some kind of marks based on some scheme, and ultimately you calculate a CGPA or a grade point average in that sense. So what we are trying to say here is that we use this kind of a scheme to evaluate different alternative locations. Now let's see how it can be done. Before, however, we do that, what would be necessary is that the various objectives that we have, the objectives we just listed out, nearness to raw material source, availability and dependability of power and so on, you have to score these objectives to determine the weights. So what is actually being suggested here is that if you construct a triangular matrix, why triangular matrix? Because if there are n objectives, there will be NC2 possible comparisons, all pairwise comparisons. So we look for pairwise comparisons. For instance, in comparing objective 1 with objective 3, you might want to give O1 2 marks or whatever the interpretation is to these marks, and then ultimately you can determine the scores by counting the number of scores or votes polled by different objectives. So you will be able to get scores. The basic advantage of a scheme like this is that when you have a large number of objectives, it's very difficult to give weights to the individual objectives. But if you are comparing only 2 at a time, it's much easy for a person or a manager to say, okay, between O1 and O3, I compare O1 as more important and the difference is medium or some such thing. So it's much easier to adopt a pairwise comparison approach and evolve the set of scores. For instance, for this particular problem, what was done was that this triangular matrix was constructed, and these were the objectives A, B, C, D, E, F, G, H, I, and the management was asked as to which do you feel. For instance, in comparing A and B, the management felt that A was more important and the difference was medium. So you wrote A2 here. Similarly, in comparing, for instance, C and G, the management felt that in the comparison of C and G, G was more important but the difference was minor. So you put minor, this kind of thing, because you are basically distinguishing between whether first you find out which one is better and then you say, okay, how much better. So this is a simple way of doing that. So having got this information, we can simply compute the total. For instance, for total A, you can count the votes in this particular row. For B, it can be in this column and this row. For C, you can count the votes here and so on. So you would know exactly what is the score or the weightage for each of these various objectives. So in this particular example, we had these objectives A, B, C, D, E, F, G, H, I, which were nearness to raw material source, availability and dependability of power, transport facilities, etc. And the total weightage given to these particular factors came out from there as 16, 4, 6, 3, 0, 14, 8, 12, 7. And this was what was basically involved here. And the weightage for all this, the percentage weightage, you sum it up. There seems to be an error here. They sum it up and then divide this by the total, and you get 23% as the weightage given to this particular factor A, and so on similarly. So 100% weightage, this is how it is finally distributed to these individual objectives. So this was a rational way of arriving at these weightages, basically using pairwise comparisons. There are a number of techniques available these days which you can employ if you so desire. AHP is one example. Analytic hierarchy process is also a pairwise comparison technique, which essentially will give you these weights and so on. But you have to go through a similar kind of an exercise. So ultimately, the results for this problem could be classified as: a survey was conducted as to where the location should be. Now the management in this case was interested that the location of the plant should be anywhere in North India. They didn't want to go to south or west or. So the major industrial districts in the north were considered, and these districts were Panipat, Sonipat, Rohtak, Meerut, Faridabad, Gurgaon and Ghaziabad. So these were the tentative locations that were possible for setting up the plant. And now we have these objectives, and these are the weightages that we have discovered, just determined from the pairwise comparisons. Finally, what we require to do is to evaluate each of these locations on these individual factors. If you recall the analogy, this is not very difficult. It's like saying, if this subject is physics, I have to give you a quiz in physics and determine the marks. I have to determine this factor, I'll find out, and so on. So what we are trying to say is that the first factor, which was the first factor was essentially nearness to raw material source. Okay. Now it was found that in this particular classification, nearness to raw material source, Rohtak was the best, right. So Rohtak got 100 points. The scheme was that the worst location will be given 50 points and the best location will be given 100 points. It's very much like trying to say that we normally don't fail candidates in the IIT, and therefore the worst fellow will get 50 marks and the best fellow will get 100 marks in the particular. So in comparing these in terms of distance to distance in the raw material source, Rohtak was relatively raw at that time, and plenty of raw material was available there and so on. So it was 100. And which was the worst? Faridabad, Gurgaon and Ghaziabad. They were all pretty low in the hierarchy, and Faridabad was the worst. Why was Faridabad the worst? Although it was an industrial town, but whatever, there was no there were already a large number of industrial units set up for this, so availability of raw material was difficult, more difficult as compared to other factors. So this was the scheme, and this is on a normalized scale of 50 to 100. Similarly, all these evaluations were done on a normalized scale from 50 to 100. For instance, in the second objective, it was felt that Sonipat was the best, and Meerut and Ghaziabad were the worst. Okay, and for instance, the third factor was transport facilities. This is transport facilities. As far as transport facilities were concerned, it was Panipat was the best out of these options, got 100 points. Rohtak was pretty good, and Faridabad was pretty good. Gurgaon was bad, and Ghaziabad was okay, and so you have this, right. So this was basically an evaluation of these locations on all the factors. So once all these scores are available, what we can do is 90 into 0.23, 80 into 0.027, and so on, and the final points that you get here are 86.1, and similarly 85.98, 91.16, 75, 61, 71, 64, etc. So from this analysis, it emerged that Rohtak was the best option out of these. Now, however, you find that this was a very good option, no doubt, but the second best option was pretty close. This is 91 marks and this is 86 marks, right. So it's like trying to say that if a company comes to recruit you, it need not only recruit the best candidate, the second best, the third best will also get jobs. So in the same sense, you find that here 91 and then 86, pretty close, and then 85.98, which is almost 86. So these are pretty close. So you could do a more detailed comparison between the first three. What this means is that Rohtak was best on 1, 2, 3, 4 out of these various objectives, whereas Panipat was best on only 2 of these objectives. Sonipat was best on only these 2 objectives. And then let's see where Rohtak was the worst on this particular factor, that is 60 marks, this one, but this was even worse on this factor, and this was slightly better, but then it was best. So on the whole, it seems that Rohtak would be the optimum location. So the optimum location was in fact suggested as Rohtak, and the company adopted this, and after many years the feedback we have received from the company is that they are very happy in Rohtak. That means the decision that was taken more than 15 years ago was probably the right decision for them in terms of whatever we did. Now, having used the decision matrix for alternative locations, you could use this methodology for any real life situation. You see, the tricky part here is how do you assign these marks to these candidates? If a particular factor is, let us say, capital cost, the highest capital cost will be the most undesirable, the least capital cost will be the most desirable, and so on. So the manner in which you assign these marks is basically the process of normalization. Now, a word about normalization. What we mean in normalization is that depending upon the objective, suppose our objective is capital cost, and we have investigated a number of different alternatives, then in the alternatives, the one which is the highest in terms of capital cost should be given the least marks, that is 20. The one which is the lowest should get the highest marks, which is 80. And depending upon, if you are not, the most convenient way to represent this relationship is a linear straight line or a normal straight line. It is very much like trying to say that we might have a teacher who is giving marks like this, or a teacher who might use a normalization curve of this kind, or a teacher who is giving a normalization curve of this kind, right. So this is exactly what normalization would mean. It's not necessarily true that normalization would be linear. Take the same example of the capital cost, for instance. We have something like this. So, if the lowest capital cost is L and the highest capital cost is H, the company might be indifferent. For instance, lowest cost might be 2 lakhs or whatever, and say up to 3 lakhs the company says no, this does not make much difference. So, you are indifferent between 2 and 3 lakhs. So, you give 80 marks to all of them who have done this particular factor, and then from here it could be a straight line, or it could be a concave function or a convex function, as the case may be. The difference between a concave and a convex function would be that in the convex function which you have here, the drop is very steep in the beginning, slope is highest here and it tends to fall, and the minimum slope is here. So, it is like saying that you are penalizing the candidate most, that is capital cost, that there is a fall in capital cost, you are penalizing him here, and relatively at this point the rate of penalty is decreasing. It is the reverse in the case of the other function. Now, what I am simply trying to emphasize here is that if you give careful thought to normalization, because this is the very important strategic decision location. And what is normalization? Normalization is, these normalization curves represent your attitude towards a particular objective. For instance, if you have a factor like labor attitudes, typically you might want to classify labor attitudes into 3 categories: bad, medium and good, or you might say restive, where the labor is so restive it is willing to pick up a danda for every small provocation. So, it is a restive labor. You have satisfactory labor, where the labor is willing to cooperate with you, and you might have cooperative labor which is willing to do everything. That's so obviously this is the best, so you give maximum marks, let us say 80. Between this you give 60, between this you give 20. So, essentially the normalization curve for such subjective factors will be a staircase function of this kind, where you can decide the length or the height of the stair in each case. It is not necessarily true that the normalization curve be linear or be portions of linear functions. A normalization curve could also be non-linear. So, if a non-linear function is there, so this is the least desirable, this is the most desirable. The most desirable aspect is given the maximum number of points, the least desirable is given the least number of points, and you can think of what would be the nature of this curve for your case. So, the point is that once we have developed the normalization curves for individual objectives, this process becomes very, very objective. All that you need to do is develop the weights for the objectives like we did through the triangular matrix, determine the normalization curves, feed them into a computer, and then feed the data corresponding to individual alternative locations into the program, and then you can get the final solution for various options. So, the idea here was that we were dealing with a practical plant location problem, a practical plant location problem which has both subjective and objective factors, and we had here a mechanism to deal with both subjective and objective factors, but there was no attempt at optimization. What we were, the kind of problem that we were considering was, we through a feasibility report looked at or identified a number of locations, and we were trying to choose the best location. So, it was a problem of choosing the best from out of the available options. That is the kind of problem that we were considering. However, in facility location we have certain mathematical models where the intention is to determine the best or the ideal location, and that particular ideal location can then motivate you to locate your facilities wherever they are. So, let us see what kinds of models. We will look at some simple models for facility location in this context. Let us talk about the problem which is known in literature as the single facility location problem. The single facility location problem is essentially the problem where you want to locate one new facility, and this problem occurs very frequently in life. Here are some examples of what we call the single facility location problem. For instance, you want to determine the location of a new lathe in a job shop. You already have 23 lathes, you bring in another lathe, the 24th one, and you are trying to find out where it should be located. It's a single facility location problem because you're trying to find out the location. A tool crib in a factory. A tool crib is the place where workers take their tools and deposit their tools every time. So it's a common facility for all workers. You might want to find out what is the best location of the tool crib such that the total travel distance of all the workers is minimized, which means total time is minimized, which means their productivity is maximized because they are wasting less time in commuting in that sense. You could talk about the location of a new warehouse for a company, one warehouse. You could talk about the location of a hospital, a fire station, or a police station, all single. You could talk about the location of a new classroom building on a college campus, single facility location problem. A new airfield for a number of bases. You can talk about a component in an electrical network. You know, electrical networks typically these days you have a large number of electrical components put onto one board. Now, suppose it is decided that improve the design characteristics, you want to put an additional resistor somewhere. Now, where should that additional resistor be, right? And it is going to be connected to some of these components. So you are trying to say where should I put up the additional resistor such that the total length of cable or the length of wire is minimized or some such thing. This is again a problem of a single facility location. You want to talk about a installation of a new appliance in a kitchen. This is again a single facility location problem. You want to find out where a copying machine should be placed in the library, assuming that in a library different readers from different locations, then you might have statistical data that on the average 20% of the users from first floor and 30% from this floor and we come here for this particular thing. So you can determine where the optimum location for the copying machine should be. Or if there is a new component on a control panel, you have a big switch gear, Larsen and Toubro switch gear, huge one, and you are trying to find out where a new component should be installed. That's also a single facility location problem. So the single facility location problem is actually a problem. In fact, that's why it's called single facility. We are not talking about single plant location, because when you recall, when we were discussing the issues in location, we had specified that we often tend to speak in terms of facilities, and depending on whichever facility it is, you have to determine the optimum location. For this problem, the statement, the mathematical statement can be built up as follows. We are saying that our variables are, we have m existing facilities at locations P1, P2, Pm, whose locations are A1, B1, A2, B2 and so on up to AM, BM. So we know the locations of the m existing facilities, and the new facility is to be located at some point x, which is xy. We want to determine this, where it should be located, the new facility. The other existing facilities are fixed, that's the assumption, and dxpi is an appropriately defined distance between x and pi. X is the new facility you want to locate, pi is one of the existing facilities. So the distance between them, we are just calling it as dx comma pi, and this distance could be defined in various ways. It could be the Euclidean distance, which is the straight line distance. It could be the rectilinear distance, which is the Manhattan distance between these 2 points. It could be the squared Euclidean distance. It could be what we call a generalized distance, or it could be a distance on a network. And in fact, this would define the variety of models which are available even for this simple problem, the single facility location problem. And what's the objective of this exercise? The objective is to determine the location x for the new facility so as to minimize transportation related costs. That is what we want to do. And what are these transportation related costs? The transportation related costs are the sum from I is equal to 1 to n, the summation of Wi into dx comma pi, where Wi is the weight associated with the ith facility, which is the product of the cost per unit distance and the expected number of annual trips between x and pi. If you recall our discussion of the Varinon frame, where we had determined weights corresponding to each of the points, so the interpretation of Wi is the same. It is a weight, it is the weightage given to the ith point. How important it is in terms of the interactions which take place between the new facility and that particular facility. So that is the objective function. This is a general problem, general statement of the problem is this. So essentially, if you look at the problem in a graphical perspective, what is really required is that we have points P1, P2, P3 and so on up to Pn or Pm as the case may be, spread out, and these are the existing facilities. We are interested in finding out an optimum location x. This optimum location x should be such that the total cost of movement between this, between this, between this, between this and between this total cost of movement should be minimized. That means what we are trying to say is that we are trying to minimize the total cost of travel or transportation between these various facilities. Okay, there could be many examples which would which we can construct. For instance, if these facilities are hospitals in the city, let us say Delhi has 10 hospitals. So these are the 10 hospitals that you have in the city, and the problem is you are trying to find out the location of a centralized blood bank facility, which can be called upon by any hospital in case of emergency, right, or whatever it is. So what we are trying to say is that what should be the location such that if you know roughly that during a particular day there are roughly 5 trips here, 20 trips here, 10 trips here, 30 here and so on, which you know from past historical data. So you can use that information to determine what the optimum location of the new service facility should be, right. Similarly, you might say, for instance, that if I want to find out the location of a hospital which will cater to the needs of different people in these localities, and if these localities have these weights in terms of number of people falling sick, right, which is, let us say, as an order of magnitude, it is proportional to population, assuming that all people are subjected to same kind of health conditions. So if you do that, then again the problem of finding out the location of this hospital is basically a single facility location problem in that same sense. Now what we would like to do is first understand the various commonly used distances that we talked about. For instance, if the location of the new facility is at x and the ith existing facility is located at the point pi, which has coordinates ai bi, then the rectilinear distance between these 2 points is actually this distance and then this distance, and mathematically the rectilinear distance will be represented by x minus ai mod plus y minus bi mod. Okay. Now the rectilinear distance is actually, you must understand that there are a large number of situations in real life where the rectilinear distance would be the appropriate one to consider. For instance, all movements within the factory are generally rectilinear, because in a factory on the shop floor you can typically move along a set of perpendicular aisles. So if a worker has to go from one place to the other, he has to take the route the perpendicular route this way and then go this way and then so that is the rectilinear distance. And therefore, if you are dealing with the problem of, let us say, machine location within a factory, or you are talking about the location of some other tool crib in a factory, or if you are talking about the location of a, let us say, even a canteen within a factory, the distance measure that you would think that is most appropriate is a rectilinear distance measure. And therefore, this is a very important distance measure, especially in the context of locations on the shop floor, locations within the factory. Of course, when you travel on cities, if you happen to travel to New York, for instance, the distances are rectilinear. That is why it is called Manhattan, right? Because in what you have is, you have a large number of parallel streets, and these are intersected by a number of other parallel streets, and all that you have therefore is movement is always rectilinear, and in fact that is the word Manhattan and rectilinear comes from there. Okay. In our context, Delhi would not be rectilinear. Yes, but if you go to Chandigarh, for instance, the movement from one place to other is generally rectilinear, because the layout of the city is such that you move about from one roundabout to another, and there are parallel streets and so on. So it is essentially rectilinear. So if you are talking about location of a facility in Chandigarh, say, rectilinear distance could be an important measure, distance measure. The next important distance that we consider is what we call Euclidean distance measure. So Euclidean distance measure is the shortest distance between 2 points. This is the Euclidean distance from the point X which you want to determine to the existing facility Pi, Ai, Bi. You have this particular distance, which is the shortest distance between 2 points. It is governed by this function x minus ai whole square plus y minus bi whole square, and the square root of this. So it can be conveniently calculated in this fashion. Where do you think Euclidean distances will be appropriate in the location problem? Where do you think you could consider? Wherever things take place, let us say generally straight line, generally, I mean, if you are trying to talk about this. That is right. What would happen is, for instance, if you are talking about the location of an airport, and you know that you are going to expect flights from a large number of cities in India and abroad here, and flights going out. So that would determine the weights for those cities, and since you travel almost straight line, so you could say that the determination of the optimum location of the airport could be. But there are other considerations in the determination of the airport, but definitely from the point of view of minimization of the total travel, this would be an optimum situation. And then where else you think this would be appropriate? Yes, it could be, but it all depends upon whether naval applications, whether you travel straight or you travel all over the sea, and how you travel, so on. So that is of course. But for instance, suppose you travel by this trolley car, kind of ropeway. Now suppose if in the mountains the government was to decide upon a picnic spot, and it was to find out the location of a trolley, a ropeway, and this ropeway could probably go either to location 1 on one hill, to a location on the other hill, at wherever it is, and at different locations as it is, then which particular location will minimize the total cost of the cableway? Obviously it will be a Euclidean distance location problem. So you could have a very large number of situations where, similarly, if you are talking about an electrical circuit and you want to fix a particular component, and the component is to be connected by wire to a number of different components, assuming of course that this will be not if it could be done on a Euclidean way in that particular component, then the location which tries to minimize the cost of wire, the cost of cable, etc., would also be using the Euclidean. Finally, let us look at this problem where you are talking of squared Euclidean. Squared Euclidean means that this under root sign is missing, so we are talking about the square of the Euclidean distance. Square of the Euclidean, so it's just this very distance but the square of it. Now, in fact, squared Euclidean distance location problems are also very relevant in many situations, and they are relevant mainly in problems which involve radiation. The radiation loss is typically proportional to the square of the distance. You may remember your thermodynamics and see that the heat loss from a particular source is proportional to the square of the distance, Euclidean distance, from that particular source. Now, this is something very, very important today, because this is in the context of, let us say, satellite location problems, or in the context of suppose you want to locate a satellite in space, and the satellite has to serve a number of existing locations on the earth. It has to serve New Delhi, Calcutta, Hyderabad, Singapore, this, that. So, you have number of m points which it has to serve, and let us say you know the weightages for these points. So, the idea is that the optimal point for the satellite would be the one if you want to minimize the total radiation loss. You want to minimize the total radiation loss, it should be located such that this particular distance, I mean basically the distance criterion is actually this particular criterion. So, or the distance measure may be any other, because you travel in any way. So, if I have to go from here to here, I can go this way, I can go this way, or I can travel on a network in any particular manner, and so on. So, it could be other or any other network, those could be other commonly used distances. So, what we do is, normally the network location problem is a very practical problem, because there you define exactly the distances from one node to the other on the network. Okay. So, you can look at the network and try to solve the location problem on the network. Now, let us try to look at this particular problem of rectilinear distances. In a rectilinear distance problem, our objective function is very simply z, which is the total cost, which is the summation from I is equal to 1 to n of wi into x minus ai plus y minus bi mod, right. That is what it is, that is what the rectilinear distance is. The only interesting thing here is that this particular function could be sort of broken up like this: wi into x minus ai mod plus wi into y minus bi mod, and which can then be written as two separate summations: the summation for x minus ai mod and the summation for y minus bi mod. And the interesting thing here is that this is a function of x alone and this is a function of y alone. So, the problem of rectilinear distances is that if you want to minimize z, what you have to basically do is you have to minimize f1x and f2y independently. That means the optimum location for the rectilinear distance location problem is determined simply by independently minimizing f1x and f2y. Now, you can determine the procedure for doing this, and rather than derive the procedure, I would state the procedure here. In fact, in this particular situation, the f1x and f2y are minimized if you locate at the median location. That is the result. That actually comes from duality theory. We can look at the proof in the tutorials. So, ultimately what happens is that let us take an example to illustrate what we have been talking about, and we will use this framework of the example on different with different distance measures. For instance, let's assume that a service facility to serve 5 offices located at 00, 316, 18.2, 818 and 22 is to be set up. It's like saying the number of cars transported per day between the new service facility which you want to set up and the offices equal 5, 22, 41, 60 and 34 respectively. So the question is, what location for the service facility will minimize the distance cars are transported per day? So it's like saying that you have collection centers for cars at 5 places in Connaught Place, South Delhi, etc., etc. And you want to have a central service facility where you will service these cars, right? And people can deposit their cars here, 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 and experience shows that the number of cars deposited per day is so much. Where should your service facility be? This is the problem, and we are assuming that the distances involved are rectilinear to begin with. So as I indicated to you, the answer to this problem is that we can determine the x coordinate and the y coordinate independently, and the x coordinate is nothing but a median location. So this simply means that if we arrange all the x coordinates in ascending order, these are 0, 3, 8, 18, 20, and this is corresponding to the existing facility 1, corresponding to the existing facility 2, this is corresponding to the existing facility 4, this is corresponding to the existing facility 3 and 5. So ascending order of the x coordinates, and determine the weights. The weights are the number of cars that come here, 3, 22, 60, 41, 34. Determine the cumulative weight. This should be 3, rather this should be 5. There's an error somewhere, it's a misprint. Okay, so you have 5, let's say 5 is the cumulative weight here, and then 27, and then 87, and then 128, and then 162. And what you do is, if the total cumulative weight, that is 162, is the sum of the weights, so half of that is 81. So you find out where the cumulative weight changes. I mean, that is, this is less than 81, this is greater than 81. So this becomes greater than 81 here for the first time. So this row determines the optimal solution. Very simple, straightforward, and therefore x star is equal to 8. So we have determined the optimum x coordinate for this particular problem, the rectilinear distance location problem, which is a merely median location. So this is how you determine the median location. Then we can do a similar procedure for the y coordinate. When you do the y coordinate, what happens is that if you arrange the y coordinates in ascending order, 0, 2, 16 and 18, you find that this corresponds to the first facility. Both the facilities 3 and 5 share this coordinate, so we write both of them here, and 2 and then 4, it's in that order. And then the weights which are there, 5, 14, so this is 5, right? In the previous slide this should have been 5. Oh, this is 5, so this particular value should be 5. Now we have 80, again you have the total cumulative weight is 162, half of that, this is less than this, this is greater than this. So where the cumulative weight first exceeds half the value, that row is here. So corresponding to this, we can identify that y star is equal to 16 from here. So it's very, very simple, right? So you observe that we can determine the x star and the y star value independently by similar procedures, by just identifying the median, and we have identified the median. So in this particular case, we now have in fact determined both x star and y star. So x star is 8 and y star is 16. So 8, 16 becomes the optimum location for the service facility. That means this will minimize the total cost of travel. That's the optimum solution, or the ideal solution for the location of the service facility for this particular problem. Now let's look at the case where you find that the distance measure is, let us say, squared Euclidean. we will not talk about the Euclidean case, we will talk about it later, but let us talk about the squared Euclidean case. That is the satellite location problem, or the location. It is also another interesting problem here. You know, it would be like trying to say that suppose the squared Euclidean problem, the optimum location is in fact in this case a centroid location. This can be proved very easily. So the centroid location for this problem is simply x star is equal to summation wi ai divided by summation wi, y star is equal to summation wi bi divided by summation wi. So for the same problem that we considered earlier for the Euclidean for the rectilinear distance case, we can easily determine this. Summation wi in the denominator is 162, which is the total weight, sum of the weights, and the x star is 12.12 and y star is 9.77. So if your distance measure is squared Euclidean, it would be best to locate the new facility at 12.12 and 9.77, and obviously this differs from the earlier median location that we had determined of 816. I was just trying to tell you that if you are still not very clear about when you should use the squared Euclidean case, suppose a set of 5-6 friends are are celebrating a bonfire in winter. Imagine this situation, and they are standing or sitting at certain locations around the bonfire. Now the question is, which is the best position for the bonfire such that the total loss of heat energy is minimum for all these guys. So if that is to happen, the bonfire should be at the centroid of all these points where these people are sitting. That is exactly the satellite location problem in terms of whatever it is. Okay. So this can be determined very simply by saying 12.12 and y star is also equal to 9.77, and therefore you can determine the centroid location very simply in this particular case. If you now look at the Euclidean distance location problem, which is the third problem that we are trying to talk about, you will recall that one simple way of solving this problem is by using the mechanical analogy that was developed by Varinon in the frame that we call the Varinon frame. Okay. All that we had done was all these points, which could be raw material sources and markets. So all the total points are actually plotted here to scale, and then you take the requisite number of strings, tie them to a common knot, pass one string through each of these holes which you have drilled here, and hang a weight equal to the weight corresponding to that particular point. Okay. And you allow the system to come to equilibrium, and when that happens, the location of P is actually the solution to the Euclidean distance location problem. As we had seen the other day, normally this method of constructing the Varinon frame and the strings model is quite cumbersome. So mathematical procedures are available by means of which you can compute this particular point, but there are certain mathematical complications in this analysis, and therefore a resort has to be made to iterative heuristic procedures for getting this particular point. So getting this point means that you start with a trial point P, and the trial point P in most of the solutions is the solution to the centroid problem. So you can start with 12.12 and 9.77 and then keep iterating in a certain fashion. We will talk about that algorithm in the tutorials as to how it is done, but essentially this is an exact solution of the Euclidean distance location problem, which you can see from here, and I think that gives you a broad idea of the how these problems are. Yes, I think so far all the problems that we have considered can be termed as mini sum problems. That means now come to the objective function. In all cases, the objective was to minimize the sum of the total travel from the facility to all other facilities, right. If you are talking about locating a central service station, so you are talking about the cost of movement from the service station to the first facility, from the service station to the second facility, and so on, and this sum was there. So all the three problems that we have considered so far were actually mini sum problems, where you are trying to minimize the total sum. Now, in many instances, especially in emergency location problems, it is not appropriate to think of a mini sum objective. It is better to think in terms of what we call a mini max objective. For instance, it is like saying that if these are the residences of different people in different localities, say, and if you are trying to find out the location of a fire station, the location of the fire station should not be such that the total cost to this plus this should be minimum, because when a fire breaks out, the fire tender has to run to that particular place. So really speaking, the location of the fire station should be such that it should be nearest to the farthest point, right. So you are trying to minimize the maximum distance from that particular node, right. So in all emergency location, minimax problems are quite common. So for the location of emergency facilities, our objective would be to minimize the maximum distance. Just to give you a motivation without going into details, for instance, if these were the points and you want to locate a facility, the idea is that what would be a minimax location? A minimax location would be try to enclose these in a circle, and the circle which has the minimum diameter, the center of that circle, which is, let us say, this one, which encloses these points. This is the circle which encloses all these facilities with the minimum diameter. This circle is larger, there could be other larger circles, and basically what we are seeking is this circle, and the center of this is the optimum location. Now graphically it is very wonderful to look at this particular procedure, and there are algorithms. For instance, there is a beautiful algorithm by Elzinga and Hearn which is actually based on this analogy. So this is just to tell you that if the objective function changes, the problem is no longer a mini sum problem but a mini max problem. Finally, let us look at this complication. For instance, we determine an ideal location by these mathematical procedures. If we determine an ideal location, what may happen is that the ideal location may not be available. There might be a building there, there might be a river running through it, or there might be other complications, and you cannot locate, because in solving the problem, in determining the ideal solutions, we have not taken into consideration the feasibility of these locations at all, isn't it? So what is interesting is that we can build cost contours. These are lines of constant cost. So this is the minimum cost, optimum location, cost increases by 5%, by 10%, by 15%, by 20%, whatever it is, and you have lines of constant cost. This will help you to choose an alternative location. These are very much like lines of constant height on a map. On a geographical map you have lines of constant height. Similarly, you have lines of constant cost, and this mapping, once it is done, would give you ideas as to which side you should shift, where is the cost lesser, where is the cost more, and there are procedures to develop the cost contours, and in fact in the tutorial exercises you will have an opportunity to develop these cost contours. Finally, let us see what we have done in this particular lecture. The main thing when we started was to look at a practical problem, a case study, and we saw that a decision matrix approach to handle multiple objectives in plant location was in fact a very worthwhile approach to consider all the objectives and consider the feasible solutions. Basically this problem could be termed as a problem of choosing the best from amongst options. That is what it all was. And then we have the single facility location models. We talked about the rectilinear distance, the squared Euclidean distance, the Euclidean distance. where the objective was to generate the best from the infinite options which are available. And finally, we talked about the notion of mini-sum and minimax problems, where the objective could change depending upon the context. And finally, we saw how cost contours can help to accommodate practical constraints, that is, moving from ideal to a feasible solution. So with this, we conclude this particular lecture, and in the next lecture we will go over to the facility layout problem, which is the next important problem in the context of facility location. Thank you.